Okay, welcome everybody to our Integrability Journal Club. And today I'm happy to introduce Florian from Humboldt University, who will tell us about integrability for Feynman integrals. Florian, please.
Yeah, thanks a lot for the invitation to talk here in the legendary London Integrability Journal Club. So this is about a sequence of papers together with these people here, Dennis Müller from Copenhagen, Hagen Münkler from ETH Zurich, and our excellent student Julian Mikchaika, who's here in Berlin. And most of this talk will be based on these three papers here, but some results are also relate to earlier work with Volodya Kazakov, Dima Chicherin, and Deliang Chong. So the motivation for what we are looking at is that, well, as many of you probably agree, QFT computations are generically hard or quickly become hard if you go to higher loop orders or look at, for example, amplitudes with a large number of external legs. And our favorite toy model is, of course, N=4 Super-Yang-Mills theory, where many things simplify. And this is, of course, due to integrability in the planar limit, which from the symmetry point of view is related to Yangian symmetry. And the question we want to ask is what this Yangian symmetry tells us about more generic building blocks of quantum field theory, and in this case, about Feynman integrals. So to tell you what I want to discuss, let me start with an example, namely the example of this one-loop box integral or cross integral, which has two different representations that I want to discuss. So on the right-hand side in green here, you have the ordinary momentum space representation. But alternatively, we can introduce such dual region momenta xj and write it in this way. And these two representations correspond to the two different graphs here. So I can either write it as a box or a cross integral. And for this talk, I will mainly be working with these x variables and only later come back to the momentum variables. So this integral is known to have a conformal symmetry. In this talk, I will talk about call it dual conformal symmetry because it's formulated in this dual x space. And this conformal symmetry implies that we can write the integral in such a form where the where this function phi carries most of the non-trivial information, and we only have an overall prefactor that carries the conformal weight.
So why X for you is a dual space? Because I would think conformal symmetry acts directly on X's.
Well, if I think about this as a momentum space Feynman integral, then X is the dual variable, right? So
X for you is momentum. Okay, that's fine then.
Yeah, I think, well, in 4 dimensions, in the massless case, I think it doesn't matter whether I think of this as a dual graph of a momentum space Feynman integral or as a correlation function. But if I go to the massive case, I would rather think about it as a dual graph than as a graph with massive propagators, because there the massive propagators would usually be Bessel functions, right? So, well, it's just a matter of notation, what I call dual and what not. But here, yeah, the x's I call dual and the p's I call ordinary variables. So using this dual conformal symmetry, I get dependence on this variable z and c bar, these conformal variables, which is already a big simplification as opposed to the generic dependence on the spacetime vectors. And then what I want to discuss in this talk is that this graph and similar Feynman integrals have this additional Yangian symmetry, which can be phrased in terms of these differential equations here. So this conformal function phi is annihilated by these differential operators here. J can take 2 values, 1 and 2, and these differential operators are written down here. And these differential equations can be solved by elementary methods. And what we find are these 4 functions here divided by z minus z bar, which all solve these differential equations. And then in addition, I can put in that this integral, as reflected by this graph here, is invariant under permutations of the external legs. So if I permute 1 and 2, the graph will be the same. And the only function that's compatible with this permutation symmetry is this Bloch-Wigner function here. So using symmetries, we've completely fixed this integral. Of course, the result was known for a long time, but the interesting point here for us is that we can use integrability to arrive at this result. And well, of course, we expect integrability to somehow completely constrain our observables.
Sorry, and this graph is finite, right? There is no divergence?
Yes, it's finite, exactly. I'm looking at the Feynman graphs I'm discussing are for generic off-shell external kinematics. So I will not have to deal with any on-shell problems that could arise. Yeah. So the outline for the rest of the talk is as follows. So first I will briefly review the integrability of massless Fishnet integrals, how this can be argued to arise from n equals 4 Super-Mills theory. I will then come back to this idea to bootstrap massless integrals using the Yangian symmetry. Then I will show that also Feynman integrals with masses, with massive propagators, have an extended Yangian symmetry, which when translated back to the momentum space can be understood as a generalization of ordinary momentum space conformal symmetry. And finally, I will discuss a massive version of the Fishnet theory, which relates to these massive Feynman integrals and their Yangian symmetry. So let's start with the massless situation. And here the starting point are these massless Fishnet integrals, which are built in a simple way. So you just have one integration vertex, which you can connect to other vertices using these standard propagators with this difference propagator structure. And then you can build all kinds of graphs which correspond to Feynman integrals, and these are generically quite hard to solve. In particular, the only explicitly solved example here is this box integral that I already discussed. And all the other integrals with generic off-shell kinematics have not been solved so far. I will discuss some progress on the double box integral in the later part of this talk. So this class of integrals is known to have very nice features. It's known to have this conformal, or what I call dual conformal symmetry. They are finite integrals. Zamolodchikov has already used them a long time ago to define integrable statistical vertex models. And it's also related to ADS-CFT integrability. So let me briefly sketch how this comes about. If we start with n equals 4 Super-Mills theory, of which we know that it has many nice properties, it's dual to ADS 5 times S5 string theory. It's believed to be integrable in the planar limit. And in addition to the two parameters, the coupling constant and the number of colors, we can introduce 3 additional parameters, namely these gamma deformation parameters. This gamma deform theory has been discussed a lot in the past. You just take the Lagrangian, replace all field products by these non-commutative products, and then the terms in the Lagrangian will get different exponential weights, including these parameters gamma j, where here the q's represent the R charges of the fields. And these additional parameters are interesting because we can now play with them. And as observed by Gurduan and Kazakov in 2015, one can take very interesting limits using these parameters. What they did was to take the coupling to 0 and then to take all 3 or some of these parameters to I infinity, while keeping these products here, g times this exponential factor, fixed. And this results in new, simpler quantum field theories where some of the fields decouple. So these theories are interesting for different reasons. In the simplest case, so in the most restrictive limit, one finds this Bi-Scalar Lagrangian here, which has here the kinetic parts and one single vertex. And this theory is distinguished because of many things, but also because it is non-unitary, because we only have this particular 4-point vertex here and not its Hermitian conjugate. So there has been a lot of work on this theory as a conformal field theory, as a hopefully solvable conformal field theory. The thing that will be interesting for this talk here is that if one looks at correlation functions in this theory, then one can argue that generically these correlation functions are in one-to-one correspondence with individual Feynman graphs. So for every correlation functions, I can only draw a single Feynman graph, which is due to the fact that this 4-point vertex here is oriented. Yeah, so I only have this combination with these arrows drawing in one particular direction. And since we know from n equals 4 super-Mills theory that correlation functions have nice properties, in particular with regard to integrability, one may wonder whether these Feynman integrals do inherit these integrability properties, because now they have this interpretation as correlation functions in the Fishnet theory. And
so you will have to add all color ordering, right, for actual amplitudes.
Yes, here I look at these traces. I look at planar correlation functions, color ordered with color ordered external x. Yeah. So when I want to ask what integrability means for these Feynman integrals alias correlation functions, I should first go back to say what I mean by integrability in n equals 4 super-Mills theory. And of course, there are different ways to see the integrability. And here the take will be to understand it as the Yangian symmetry that underlies many different situations. So just briefly, what is the Yangian, which of course many of you know. So we have a Lie algebra G, which is generated by these standard Lie algebra generators here, which have an ordinary tensor product action, this trivial coproduct here, and obey these standard commutation relations. And in addition to this, we have a set of so-called level 1 generators, which are defined in terms of the same densities of these level 0 generators, but now we have a bilocal action. So we take two densities acting at point j and k of the tensor product, and we sum over all relative positions here. And of course, in n equals 4 super-Mills theory, this Lie algebra would be PSU 2,2/4. So if we think of the integrability of n equals 4 super-Mills theory in this algebra, then we would wonder whether these Feynman integrals inherit this symmetry. And indeed, this is the case. These Feynman integrals are invariant under a conformal version, a bosonic conformal version of this Yangian algebra, which in particular means that they're annihilated by these non-local level 1 generators here. And this can be shown using monodromy, which is a generating function for the Yangian generators, and which is, as usual, defined in terms of such Lux operators that depend on a spectral parameter and a conformal dimension. And if you introduce this graphic notation in terms of these arrows for these Lux operators, then one can act with this monodromy on a Feynman graph by acting here on all the external legs. And then there are certain rules which allow to pull this monodromy through the graph and thus to completely disentangle it from the graph, which results in such an overall eigenvalue factor, such that this eigenvalue equation then implies the invariance under the the level 1 Yangian generators.
Could I ask about n equals 4? So what are the actual status of Yangian symmetries there? Because does it go much beyond 3 level, for example?
Well, of course, in n equals 4, it's more difficult because beyond 3 level, the amplitudes are divergent. But, well, still people have defined these finite remainder functions. And I think in particular there, this Q bar equation is what corresponds to the Yangian symmetry, and which in fact also relates different loop orders of the amplitude. So, well, I think there is this notion of Yangian symmetry, which is a bit more hidden and more tricky because the amplitudes are divergent. But well, in principle, I think it's also more powerful because it relates different loop orders.
But are there like understanding on how this Yangian symmetry actually relates to integrability, which we know like from anomalous dimensions? Is it coincidence? Are they independent symmetries or?
Well, at 3 level, I think one can explicitly understand it. There you can understand the 4-point scattering amplitude as the density of the dilatation operator. So you can really formulate the spin chain problem using form factors, such that really the Yangian symmetry of the 4-point scattering amplitude corresponds to the Yangian symmetry of the 1-loop dilatation operator. At higher loops, I don't think this has been done explicitly because it's much more complicated due to the divergences. But I think in principle, it should be possible at some point. Yeah.
Another question. Why did you switch to Euclidean conformal group SO51 instead of the SU22, which is inside the super algebra?
Well, because it's simpler to treat for the examples I've given. For example, this box integral I discussed at the beginning, I use these permutation symmetries. And if I go to Euclidean, to Minkowski kinematics, the permutation symmetries will not all be there. It depends on to which kinematical region I go, which permutation symmetries this integral has. And the expression for the result will also look slightly different. So, well, here the answer is, it's just the simplest case, and that's the case I want to start with to understand how Yangian symmetry yields Feynman integrals, but I think the same applies also to the Minkowski case. It's just we have to be a bit more careful.
But at the end, you have to switch back to the Minkowski case, not?
What do you mean? I have to? It depends on which Feynman integral I want to compute. At the moment, I just want to understand this mechanism of getting Feynman integrals from Yangian symmetry. If I want to compute the Minkowski Feynman integral, yes, of course, I would have to do that. Here, I'm looking at Euclidean integrals.
Okay.
And could you explain this notation of the delta n minus 1, and u?
Well, u is a... Sorry?
Yeah, because un.
U is a spectral parameter. So each Lux operator depends on 2 variables. Delta is the dimension that enters the representation of the conformal generators. And U is a spectral parameter.
Yeah, like for spin chain, normally T depends on 1 spectral parameter. It's like, right?
It's 1 spectral parameter and 1 conformal dimension. I mean, in the dilatation...
Because you have un and this vector on top of u. This maybe it's, I don't know, maybe I misunderstand notation.
Vector on top of u, where?
T of u.
Oh, because the monodromy depends on the vector. Each Lux operator depends on 1 un. Okay, you say the monodromy only depends on 1.
Maybe it's just in homogeneities. UN play the role in spectral
right, okay.
parameter and in
I shouldn't call
homogeneities
each of them a spectral parameter, but it's true. It's in homogeneities, and there's 1 overall spectral parameter. Yes.
Mm-hmm.
Mm-hmm. But each depends on.
Could you maybe explain still a bit this notation? What is the auxiliary space here? And also, what do you diagonalize when you write eigenvalue equation? The trace or what?
No, it's not the trace. It's you act with the full monodromy. And where there's a diagonal matrix here in front, yeah.
That's not really like in spin chains where you really diagonalize trace of T, right?
No, it's not the trace. It's really the monodromy, because you want the Yangian generators and not in the spin chain. If you take the trace, you get the local charges if you expand it, right?
But then it seems you are saying that all components of T commute with each other. Like for spin chain, they definitely don't commute with each other normally. Because you're saying this Feynman diagram diagonalizes all components of T.
So what is the auxiliary space? How many components does it have?
I mean, the expansion of the monodromy you see here at higher orders gives you all the Yangian generators that annihilate the integral. Yeah. So what remains is only this one at leading order.
No, well, I'm not saying that it's incorrect or anything. I just trying to link to what I know, like from spin chains. And for spin chains, I would be a bit surprised if all components of T commute with each other, because like it has B operator, which like creates magnets, and then there's transfer metric.
Why do they have to commute with each other? I don't.
No, because you are saying that they all have the same wave function, which is this Feynman diagram. So I mean, maybe they don't totally compute, at least they have invariant subspace, or they have common wave function, right? The common eigenvector. It's like, I don't know about any similar situation in spin chains where that would happen.
Okay, I see.
Or related question, what is order here? So you wrote it with some order, yes, so, and you have 2D lattice, so how you order it, dots?
No, but like it is a disk topological, so ordering is kind of fine.
No, but it is exactly about commutativity of this guy. So it's about what you asked, yes? So you say that they commute, and if they commute, there is no question about ordering, but if not, then the question, what is ordering on this 2D lattice?
You mean the ordering of the Lux operators?
Yeah.
Well, my question was about T's, right? So if you have T of U and T of V and different matrix elements, why would they commute with each other? So normally
T of U and T of V in general, they don't commute, no.
Isn't this the thing that they're just all zero?
But I mean, it's still a common eigenvector, right? Even if it's zero.
The thing is a singlet. It's like one-dimensional. So
even worse if you consider all possible initial and final points of this loop, right? As Julius was saying.
Yeah, I mean, you can break in different places. So they all commute, even no matter where you start and end, and which index you start and end.
I mean,
it's just very unusual from the spin chain. So I don't know, maybe the intuition from spin chain doesn't really apply here. But
yeah, it is. It's different, right? It's that like they annihilate. Well, like the Yangians annihilate the amplitude. They're not spectrum generating.
Yeah, but if I build like T for a spin chain, will I be able to find a vector which is annihilated by all components of T? I don't think so.
No, that's right. The spin chain is not.
If you have like dual representations, I mean, if you have different representations at the sides, then you can find this type of eigenvector.
So you need different representation of the size.
Yeah, like a dual, like if you have SU3 and you take fundamental, then you need some anti-fundamental as well to build singlets somehow. Yeah.
So it will annihilate all elements of Tij for any.
Yeah. There's like the transfer matrix eigenvalue will be 0, maybe, or will be the rank of the will be n for SUN.
Yeah. So yeah, but okay. So I mean, some intuition fails. Maybe we just continue.
Well, I think in general what you say is true, that when you come from the spin chain, there's no state that was annihilated by all of PSU 2,2/4, right? There
Yeah.
was no, and the amplitudes are exactly that thing that is annihilated by all of the generators. So yeah, it's really not, in that sense, it's a bit orthogonal, yeah.
And then I don't know if we again use this comment of Ruben that for some spin chains with different represented different sides, there are such vectors. Is it vector? Would it be unique, this vector, or how constraining this requirement in another way? Ruben, do you know if it's unique such a vector, like or not?
I think it's yes, it's unique, and it's the partition function of the lattice in the end, right? I mean, if you fix I mean, you take this lattice that he has there, yes, and you fix and then you at each side you can have different components, so you can fix the boundary conditions and you compute the partition function. This would be one number. So this vector that you're looking for has at each entrance one partition function for one boundary configuration. So it's unique.
Yeah, okay, but let's move on because I don't quite understand what you said and it needs more discussion. Yes. Maybe we discuss during the tea break.
Well, yeah. The example I've shown at the beginning was that at least for this box integral, we find 4 different solutions to the Yangian invariance equations. So if Ruben says in some sense it has to be unique, then I don't know, I guess there has to be additional information to make this link. Okay, let me continue. So this is I'm still just at the review stage. Okay, so it's not only these square lattices that have these properties, but you can also look at different dimensions where you get different lattices. So in position space, the natural propagators would have this structure here, which lead to different lattices. If you require that at each vertex, the propagator powers sum up to the space-time dimension, which would give you the conformal symmetry. And in fact, you can also treat the dimension as a generic parameter and then find similar statements if you also introduce generic propagator weights that sum up to this generic space-time dimensions. So now that I've shown you that there are these examples of Feynman integrals, so each graph that you could cut out of these lattices has this Yangian symmetry. The next question is, of course, what does this Yangian symmetry imply, and can we use it somehow? I already have shown you a brief example for this at the beginning. So let's just look in more detail at what it means. So I told you there are these level 0 and level 1 generators. The level 0 generators take this form. It's these differential operators and the x variables, dilatation, Lorentz, momentum, and special conformal generator. I want to impose this condition that propagator weights at each vertex sum up to the space-time dimension, which means that these Feynman integrals are annihilated by these level 0 generators. And this again implies that I can write the integral as such a function of a lower number of variables. And then I've used my dual conformal symmetries, or the level 0 symmetry of the Yangian. If I go to the level 1, it's interesting to note that one level 1 generator, in addition to the level 0 algebra, is sufficient to get the whole Yangian. And here, for example, you have the level 1 momentum generator that's written down in terms of the same density. So these are the densities of the level 0 conformal generators. And it has this bilocal action and some local tail here. And one can evaluate these equations here, these invariances, under the Yangian generator, and we write them in a certain form. So we take out an overall prefactor that carries the conformal weight, and we write it in terms of these particular vectors here, which are then multiplied by some differential operators, which I call PDE. And at least up to a certain number of points, up to 6 points, one can argue at least that these differential operators annihilate this conformal function on their own. And like this, we can relate this Yangian invariance conditions to a set of differential equations. So if we now look at an example again at this box integral, but now with or cross integral with generic propagator power. So here I've introduced now A, B, C, D, which sum up to the space-time dimension to have dual conformal symmetry, which then tells me that I can express the integral in terms of these U and V variables. And then I can translate the Yangian invariance into differential equations. And what one finds are these two differential equations in U and V, where for convenience, I've introduced these shorthands here in terms of the space-time dimension and the propagator powers. So now one has two options. Either one can solve these differential equations, for example, by making a series ansatz, or one looks at this old book here where they are discussed in quite some detail, and they are known to be the defining differential equations for this Appel hypergeometric function F4 that's written down here. So this series solves these differential equations, where here I've used the Pochhammer symbol, which is just this ratio of gamma functions. So I know that this integral should be expressible in terms of this Appel hypergeometric function. And in fact, there's the solution space is spanned by 4 different functions that can be written in this way. So they all can be expressed in terms of F4 or shifted versions. So where the parameters are shifted of F4, and all these 4 functions solve the differential equations, which corresponds to certain symmetries of these differential equations. So we can make an ansatz as a linear combination of these 4 functions, and again use the permutation symmetry of the diagram. So if I swap leg 1 and 2 and at the same time the weights A and B, this is a permutation symmetry, and this fixes the coefficients C1 to C4, which gives the whole result. And if I take the propagator powers to 1, I find again this Bloch-Wigner function that we've seen at the beginning. And also if I take a 3-point limit, I send one of the points to infinity using a conformal transformation, one finds an old result by Bose and Davidichev, who computed this integral by other means. So again, this integral was known before, but for us, the interesting statement is that we can use it even with these generic propagator powers using its symmetries. Of course, it would be much more interesting to look at examples which are not known. And here the next to simplest example of these square fishnets is this double box integral, which of course has a much larger number of conformal variables as opposed to the box integral, which had 2 variables. This conformal function here has 9 variables, and this is also reflected in these differential equations that we obtain from Yangian symmetry. So these differential operators here annihilate the respective conformal function, and here I already have used a lot of notation to package this on this slide. So I introduced these Euler operators here, which I then again packaged into these shorthands here. So these are much more.
Could I ask?
Yeah.
So in how do you fix this time which of the 4 solution of the linear combination of 4 solution is the correct one? Before you were using symmetry, right? Between
yes,
legs,
yes.
But now it's probably broken.
I will show you that I don't fix them, and it's not only 4 anymore. This is on my next slide. So this is, of course, a big step. So here is what I can say about this double box integral, which is naturally related to the hexagon integral. So it makes sense to discuss them at the same time. So this hexagon here can be obtained by taking a derivative in one of the cross ratios of this double box. That's why I put them on the same slide. And in fact, here we don't only find a basis of 4 solutions, or actually for the box, I haven't shown you this, you have 12 solutions if you go to different kinematic regimes. The 4 solutions I've shown you are in the regime where u and v, the conformal variables, are small, but you could also express it in terms of u over v and 1 over v. Then you have 4 different solutions. So for the box, it would be 12. And here this corresponds to roughly 5,000 for the double box and 2,500 for the hexagon, which are all formal solutions of these Yangian equations. Yeah. And of course,
these are solutions which are formal series solutions.
Formal series, yes, exactly. Yeah. And yeah, as you noticed, we won't be able to fix this using the symmetries of the integral. So it seems to look at this algorithm and to go from 2 variables to 9 variables is a really big step. Fortunately, there was a nice paper in the meantime by these gentlemen here who looked at these series and the Feynman integrals we wrote down, and they were able to fix this linear combination using some multidimensional Mellin-Barnes approach. So they really wrote down explicitly these combinations here in terms of 44 series for the double box and 26 for the hexagon integral. So far, they only have a short paper out with 5 pages plus 20 pages appendix where they present the results, and the details are announced for the future. So it will be interesting to see how this interacts with this Yangian approach. From our viewpoint,
could I ask, could you like use some kind of OP limit and fix some of the combinations by some, essentially like bootstrapping it to some extent?
OPE limit. What?
Yeah, like bringing 2 legs together.
And... yes, you can do this. In our paper, we also have discussed some of these limits, but I don't think they will fix this linear combination, because there are, where you see it's a linear combination of 26 series. You will have to fix 26 coefficients. I don't think one can find them in this way. I think here I'm looking at off-shell integrals, right? The external kinematics are off-shell. I think this is still a missing piece in this Yangian approach. We also have to think about the situations where the particles are on-shell, and I think exactly at these configurations, the symmetry will be slightly broken, such that one has to deform the generators, and this should give some additional information. At least in the context of tree-level amplitudes in n equals 4 superannuated theory, this was how it worked. And I expect that also here, this is additional information that we need to really fix this linear combination. Well, from our perspective, this step from 2 variables to 9 variables is just a bit too big.
Florian, can I ask? I'm lost in this slide. So you had predicted that it was a linear combination of 5,000 terms. And then what did these people do? They showed that they could reduce to 26 terms? Or it's unrelated, or the computers different method?
Okay, first for the box integral, yeah, you've seen I can write it as a linear combination of 4 functions, 4 series.
But then you said that was cheating. It was actually, you had forgotten to tell us that it was small cross.
No, but it's not cheating. I understand why it's only these 4 functions. It's these 4 functions because they're the series where the natural series variables are u and v. In the other case, for the other 8 series, the expansion is in u over v and 1 over v. So it only converges when these series don't converge when u and v are small. So that's how
that could be an example of you start with 12 and you get rid of 8 right away by an OPE argument, right? Because they would not have a good OP, right? So that's related to what Colli is saying, right? So out of these 12, you kill 8 right away.
Well, yeah, right. They wouldn't convert.
So you could kill also
exactly.
a lot from your 6-point case, right? You could very likely kill almost everything, right? Most of them will probably also not have a good OP, right?
Another problem here for the 6-point case is what are the good variables to write down the series? I mean, you can choose all kinds of cross ratios or combinations of them, and
Well,
it's
Pedro
not
explained us last time the best ever variables with it, right?
Of course.
Well, okay, I think that's another question. Do we have the right fundamental solution, which we then shift somehow to get all the other series? Yeah. But okay, back to your question. So I have these 12. I can distinguish 4 which converge in this region, and then I can fix the linear combination. And similarly, in the 6-point case, we can look at the differential equations. We can somehow find one series that solves them. And from this, we can argue that we can shift basically these summation lattices, yeah, in certain ways, such that they don't spoil the fact that this series solves the differential equations. And that's how we can come to these numbers here, yeah. And then we have all these series, but well, we didn't even think further because we didn't have enough symmetries to fix them. So we thought, okay, we need some better way to refine these algorithms. And what they do explicitly, I do not really know, because as I said, at the moment they present the result and they say they will give the details in a follow-up paper. They use Mellon-Barnes techniques for multi-scale, multi-variable problems that they have looked at in the past for 2 or 3 variables, I think, and they now managed to extend it to more variables.
But then let me just understand the statement in this slide about these equations. These h's, they are not known functions. They still have unknowns. Is that the statement? I'm not sure I understand your definition of h, because k appears on the left-hand side. On the right-hand side, there are other variables. Are these h's known functions?
H's are known, but the coefficients are not known. At least we didn't know the coefficients, and they now give the coefficients.
So all these coefficients are 1. It's like 1 times h1, 1 times h4. So this is not.
In total, it's 2,530 series. Some of them are 0, some of them are 1. And it seems, well, they can also write apparently different combinations of 26 series. You can not only take these 26, but you can also take other combinations of 26 series.
So they are not independent. They could.
Yes, but this is already the case for the box integral. You can use some analytic continuation formulas to go to different kinematic regimes, so they are not really independent.
So they solved the problem. They computed the double box.
Seems like, yeah, well, they give the result. This is for generic propagator powers, yeah. So it can still be difficult to take the limit propagator powers to 1.
Okay.
Or subtle at least, because these coefficients sometimes diverge. Well, here the coefficients look like they were well behaved, but yeah.
But if each of these functions, is it true that each of these functions is like a 9-fold sum?
Yes, that's true.
And it looks useless, no?
Well, it's formal, yeah. It's a formal result, I would say. But you have to start somewhere.
Okay.
Well, as I said, I think one question is how do you choose these double W's, yeah? We've chosen it in some way, and they use the same variables, but there are tons of different versions you could take, and it's not clear what one is the best. Okay, what we did was to start with the box and then try the next to simplest square fishnet integral, which was a double box, which is known to be very hard and, well, not the best to refine our algorithm, apparently. It would be much nicer to have more parameters to play with and not to have to add an external legs or even 2 external legs to go to the next to simplest example. Yeah. And this brings us to the finally to the massive situation.
Sorry, so another suggestion. If you bring 2 legs together, then you get this ladder integral, right? Which has tons of coefficients for you to fix.
Yeah, yes. If I bring these 2 legs here together, I get the ladder integral, yes. But and these 2 at the same time, right?
Yeah.
These two,
and but then it's the whole function still of the cross ratios. So it
then it's a
would
function
fix
of
quite a few coefficients.
yeah, one can do this analysis, of course, but well, take this.
But this may require
limit.
like analytic continuation because your formal series may not converge in this limit, and then
Exactly,
right?
exactly, yes.
Mm-hmm.
Yeah. So I think
may I also ask a question, Florian? I mean, what is a philosophical question? You had 8-fold integral, and you get the result in terms of 9-fold sum. What is the progress? You added one more operation.
I agree that it's a formal thing to understand it. I mean, in the end, I think the most interesting case is, of course, if we have propagator weights 1, and to go back to some polylogs or generalizations of that. That's what we started with for the box integral, and you see that you get the Bloch-Wigner function. Then we've seen, okay, if we generalize it to arbitrary propagator powers, we get this series. And in fact, for us, it was much simpler to solve the equations in terms of this series, because there we have an algorithm. And now we are trying to explore where this leads, which series are there. But I agree. You get a sum that in the end may be more difficult to evaluate than maybe a Feynman parameterization of the Feynman integral. We are still understanding this, yeah.
Okay, maybe actually it is a good point to go to start coffee break. We actually already more or less in the stage of coffee break.
Yeah, we almost have half of the talk, right? So
yeah, Kolya, maybe you can pause the recording and we will proceed with this.
Okay, so well, we've seen that this approach here leads to some formal solutions of the Yangian equations also in the 6-point case, but yeah, to fix this linear combination seems a bit too hard from this perspective, which means that to go from 2 to 9 variables is a too big step, and it would be better to refine this algorithm on simpler examples where maybe we can better tune the number of variables. And this brings us to the idea to maybe introduce some masses, because if we switch on a mass, then this will just increase the number of variables by 1, and not like if we switch on another external point by, I don't know, 3 or 7 to go from 4 to 5 or 6 points. Yeah, so, well, of course, the most natural idea is to look at how these things came about in the massless case, and there the starting point was n equals 4 super Mills theory, and via this gamma deformation, one arrives at the Fishnet theory, and one can argue that Feynman graphs have this symmetry. So why not do the same in the massive case and look at n equals 4 super Mills theory with masses? And of course, we can give a VEF to one of the scalars, which people have looked at in the past, which then modifies the propagators in this way. So before I had these 1 over xjk square propagators, and now I just get the masses, which can be interpreted as a 5th dimension. And the resulting scattering amplitudes of Feynman integrals are known to have a massive extension, or this 5-dimensional extension of dual conformal symmetry, which is generated by this straightforward 5-dimensional generalization of the generators. However, there's no known massive Yangian symmetry in this massive phase on the Coulomb branch of n equals 4 super Mills theory. So even if we would start with this massive theory and would then take a similar limit, we could not really argue that the Feynman graphs we find should have Yangian symmetry, because already at the starting point, we don't know that there is a Yangian symmetry. So what we then did first was to look at Feynman integrals directly with masses. So this graph is just to introduce the notation. So now we have solid propagators, which correspond to massive propagators, and dashed propagators, which are massless. So this, for example, is a 2-loop integral. Yeah, and the black lines are again the X space graph. The green lines give you the momentum space graph. And what you can do is to build the Yangian generators as we did before, but now based on this massive version of dual conformal symmetry. So we plug in here the same densities, including these masses. And again, this level 1 momentum generator, for example, takes the same form as before, just with different densities here. Just
so
one
could
thing.
I have a bit naive question? So when you have this diagram, right? So in principle, you don't need to like know about Yangian and so on. You can just say, okay, let me annihilate all this external propagator with like green, I mean, with the, you know, with a box plus m square, right?
Okay.
And then I get some differential equation on this diagram straight away.
You get some.
Is it like included into Yangian, or it's more than that, or what the relation?
I would say it's not included, no. That would give you an inhomogeneous differential equation, right? Here we have homogeneous equations.
Yeah,
so,
well, if you act, I don't know, 3 times, then you will get only delta function. So if points are different, you can say it is homogeneous in some sense. Right? If you ignore the complex terms.
not sure I understand. If you,
I mean, if all the points are at the different location and just kill propagators, so then you will just get. Okay, so you get this internal propagator. So you're saying it's inhomogeneous. Okay, I agree with that. Probably. Do I? No. Yeah, I do.
I mean, so you want to act on these propagators here in the integral, right? Get a delta function which localizes the integral. So if you do this with 2 propagators, you can localize both integrals, but still you will have a non-vanishing term that is the inhomogeneity of the differential equation, right?
Yeah, so I thought maybe if you act once again, then okay, you kill it totally, and then it looks like homogeneous equation.
I see, but then.
But I mean, it would be good if it's not included, right? Then you can include this extra constraint.
Yes, I think you can use that as well. And maybe that
But
this
probably it doesn't commute with this power series.
Oh, it is probably good. Could be even more constrained if it doesn't commute.
Well, of course, people have used these differential equations that you mentioned to compute Feynman integrals, but to me, it's not clear how it's connected to the Yangian. And at the moment, I think our problem is not that we have, well, not enough differential equations. Well, maybe to fix the linear combination, it could help. I don't know. We haven't really put this in as an extra constraint for the 6-point integrals on the previous slide. But I think it's not included in, at least not in this form of the Yangian we've written down here. So in the massive case, just to repeat, I want to construct the level 1 generators in the same way, just using these massive densities. And well, this is just a bit ad hoc. I write down the same generators. Here I have naturally now a space-time index that runs over 5 dimensions. And also here I would usually have this nu would be summed over 5 dimensions if I would just write down the thing as a 5-dimensional level 1 generator. But I want to introduce this summoned over the 5th dimension over the well, if d is 4, it would be 5. Here it's d+1 over the d+1st dimension as an extra generator. And you will see why this is useful, because it's gives you an additional symmetry. We can just treat it as a separate generator. So what we then did was to act on massive Feynman integrals, and surprisingly we find that at one loop, actually all of them have this Yangian symmetry, this level 1 symmetry, even if we include these masses. And even more so at one loop, it's not only the integral that's annihilated, but even the integrand. And even this integrand is even invariant under the 2-point density of the Yangian, which essentially means that this is a property of the propagator. So it's something like the propagator obeys some kind of RLL relation with the Yangian Lux operators. And this extra generator that I've shown you above is also a separate symmetry. So you have actually really a lot of differential operators that annihilate this integral. So these are actually so many that you might wonder whether it's really something related to Yangian symmetry or whether there's some more general invariance statement that should be made here. But if we go to two loops, things are more constrained. And what we can show here is that we can still write down a lot of Yangian invariants, namely those that are constructed from an L-gon and an R-gon, so a one-loop graph with L-legs and a one-loop graph with R-legs, and we glue them using such a massless propagator. Yeah? So the important thing is that the internal propagator is massless, while the external propagators can be massless or massive, and we can even analytically prove that these have Yangian symmetry using also the symmetry of the one-loop integrals. Here it's no longer the integrand that has this property, but really only the integral. So this shows that it's a more fine-tuned thing than at one loop order, where we really have a more general class of annihilators. And also this extra contribution to the generator is no longer a symmetry at two loops. But we also see that it's a quite general statement, because if you go to the massless limit, so make all propagators massless, it's really almost all one and two loop integrals, planar one and two loop integrals that have the symmetry. The only thing you are not allowed to do is to put these two coordinates here on the same point. So to build something like build something like these ladder integrals that Kolja mentioned before. There we don't really know how to formulate this symmetry, but in principle it's quite general, and a quite general statement also at two loops. So how about higher loops? There we don't have any analytic proof anymore, but we have looked numerically at several integrals, written down the Feynman parameterization, acted with the Yangian generators, and looked at whether these integrate to zero or not. And based on this, we conjecture that actually all graphs that are cut from regular tilings of the plane, so similar as in the massless case, have this symmetry, but now all these external propagators can be massless or massive. So we can switch on massless here. The important thing is that the internal propagators, the dashed lines here, remain massless. And well, we've tested this on these examples here, which are cut from regular tilings on the left. And we also checked some irregular graphs that are not cut from regular tilings, where we don't find that this procedure yields zero. So one thing I haven't yet told you is one ingredient of these Yangian generators, namely this evaluation parameter here, which relates to these inhomogeneities of the monodromy we've seen before. And these evaluation parameters are fixed by looking at the graph. So you pick one arbitrary leg and set the evaluation parameter to zero. And then you can walk clockwise around the Feynman graph and obtain the other evaluation parameters by these rules here. So if you walk from this to this point, for example, you walk along this propagator, you pick up a minus aj/2. Aj is the propagator power, and along this one, and you pick up a minus aj+1/2. So you walk around the boundary and you pick up additional contributions, and that gives you the j plus first evaluation parameter. Similar here, you pick up this aj/2 from this propagator, you walk along an internal propagator, which gives you a contribution minus bk plus d/2. Bk is again the propagator power, d is the space-time dimension, and then you walk along this one, which gives you another aj+1/2. So there's a...
So there's no mass dependence, right?
Sorry?
There's no dependence.
No. It's just fixed numbers, yeah.
Is it hidden in generator G? Because I missed this, I think.
The masses.
The masses.
Yes, exactly.
Okay.
They include differential operators with respect to the masses. Yeah. So this is something we put in also for our numerical tests. So we fixed these particular evaluation parameters which work for the regular tilings, but don't give an invariance for the irregular graphs. So here's a summary of the integrals, of the symmetries, of the integrability properties we find. At one loop, all n-gons have full Yangian symmetry if this dual conformal constraint here is obeyed at each vertex. Well, at one loop, there's only one vertex. And we even have these extra generators that annihilate the integral. And at two and also higher loops, we have the full Yangian symmetry if we have this conformal constraint obeyed. An interesting thing is that we can also give up on this dual conformal constraint here. So we can give up on the constraint on the propagator powers, which brings us to this column here. And the interesting thing is that at one loop, we still have all of these level 1 symmetries, even if the level 0 symmetries are broken because we don't impose this. And at higher loops, we still have this p-hat symmetry. So this p-hat really plays a distinguished role and appears even if it's not embedded in the full Yangian symmetry. So what does this mean? Why is there this special generator that can that is a symmetry even beyond dual conformal integrals? And what we did here was again to look at the massless case where we know that the Yangian algebra can be understood as a closure of this dual conformal algebra and an ordinary momentum space conformal algebra. So you have two conformal sets of conformal generators that act on momenta or the dual momenta, which generate independent symmetries. And if you commute them, you get the Yangian. So what we did is to take this massive level 1 momentum generator and translated it from these X space variables to the momenta defined via this equation. And we find that the level 1 momentum generator can be translated into this K bar, which actually forms part of this momentum space representation of conformal symmetry. And the novel feature here is that it includes a contribution that acts on the masses in this slightly non-local fashion. Yeah? So it acts on nearest neighboring masses of the Feynman integral, and the statement that we've seen this level 1 momentum generator here appear even if dual conformal symmetry is broken means that this massive generalization of the momentum space conformal symmetry has a life on its own. So you can give up dual conformal symmetry and still have this massive version of momentum space conformal symmetry. So I announced this approach to go to the massive situation because we wanted to refine this bootstrap algorithm. So let me give some examples here. And in fact, here we can now look at much simpler integrals, like, for example, this bubble integral here with two external legs, which using this dual conformal symmetry depends only on this conformal variable here. So I can write it in this form here with some function phi that depends on this variable. And the Yangian differential equation that we find is just this differential equation, which is well known to be the differential equation for the Legendre functions of the first and second kind, which are these P and Q here. And then we can just evaluate some numeric data points which fix the overall coefficient. So up to this coefficient, again, we have fixed this integral from the symmetries. And this, because of the masses, we really have now a one variable case where we can study this algorithm. Before it was the box integral with two variables. That was the simplest example. Another example is this triangle integral, which imposing conformal symmetry depends on three conformal variables, which are these ratios here. We can write down the Yangian PDEs, make a series ansatz, And what we find are actually 29 formal solutions of this ansatz, but only one of them is naturally written in these effective variables u, v, and w. So only one of them converges for small u, v, w that corresponds to the regions, kinematic regions we already discussed before. And in fact, we find this series in some older papers. It's due to Srivastava and who called it HC. And since we can argue that only this series of the 29 formal solutions has the right convergence properties, we said, okay, the integral should be expressible in terms of this function. And again, using numerics, we can indeed fix the overall coefficient to have this form. And well, to our
look
knowledge,
very numerical.
Sorry?
The coefficient doesn't look very numerical.
Well, yeah, we put in some random exponents here and random masses, and then figure out this factor. So it's always, yeah, we can never fix the overall factor using these Yangian equations because they are homogeneous, right? So this we have to put in somehow differently. Yeah, to our knowledge, this expression for the integral is also not known in the literature before. So it's a nice relation between this integral and a single hypergeometric series. So finally, I want to come back to the question why there is this massive integrability of these Feynman integrals. The first idea was to look at massive n equals 4 superpower Mills theory and take a similar route, but as I said, we don't know of any Yangian symmetry in massive n equals 4. So how should we deduce from that Feynman integrals have Yangian symmetry? So now let's go back to this. You have a question, Kolja?
So in relation to that, so if you start massless case and other Yangian generators you use there are exactly the same as n equals 4, I just don't remember really.
Well, it's only here we are looking only at the conformal algebra, not at PSU22/4, right? So,
yeah, well, okay, if you take the sub Yangian, whatever.
Yeah, then it's the same essentially. Yeah, usually in n equals 4 we don't have these evaluation parameters, so this local tail that the Yangian generators had. And in n equals 4 it works out without the evaluation parameters because the dual Coxeter number of PSU22/4 is 0. That's a special feature of n equals 4. If you go only to the conformal case, you need the evaluation parameters for consistency because the dual Coxeter number is not 0 anymore.
So where the geometry is encoded then of the diagram in n equals 4? Because before we discussed that they totally encoded into the inhomogeneity.
Well, in n equals 4, it's not really the diagrams that have the symmetry, but only the amplitudes. It's a sum of diagrams, right? Mm. So, yeah, it's not so directly related to a Feynman graph.
Yeah.
Okay, so let's ask the question where this massive integrability comes from. And well, here the natural question would be whether we can define a massive version of the Fishnet theory, which allowed us in the Massless case to argue that the integrals have this Yangian symmetry. And our first idea was to look at spontaneous symmetry breaking in the massless Fishnet theory. So to take this normal root n equals 4 gamma twisted n equals 4 with the double scaling limit, which yields this spontaneously broken Fishnet theory. So we can either take the double scaling limit first and then introduce the VEF, or first introduce the VEF or take the double scaling limit. This yields the same spontaneously broken Fishnet theory, which was also studied by Volodya and company. For us, the important thing is that this theory, this procedure leads to propagators of this product structure. So the masses don't enter as differences, but as products. So these are not really the Feynman integrals for which we found the Yangian symmetry above. So for us, this means that somehow this is not the right theory to relate Feynman integrals to integrability. Still, this theory is interesting for different reasons, as shown by Volodya and company, because it allows for some natural symmetry breaking. It's a non-supersymmetric theory which has conformal symmetry breaking, where still some of the vacua survive the quantization. And in this theory, we also have particular soft theorems for scattering amplitudes. So in the broken phase where the masses are introduced, you still see the conformal symmetry of the original theory in soft theorems for scattering amplitudes.
But you also need the selection rule for this tiling thing, right? So whatever is this underlying theory is, it should also select this particular graph.
Exactly, yes, that's true. We thought, okay, how can we get a massive theory that has the right Feynman integrals? And that brought us to the idea to take the double scaling limit directly on the Coulomb branch of n equals 4. So to commute these steps here, which lead to an alternative theory, which now really has this difference property for the masses in the propagators. Yeah. You could say, okay, why is this not the most natural thing to do? Why did you not first think of that? And the critical step here is this gamma deformation. So we want to start from the Coulomb branch, n equals 4 Lagrangian, introduce gamma parameters, and then take a double scaling limit. Yeah. But the gamma deformation, which can be thought to be generated by this bilocal exponential operator, is in principle only well defined on R-symmetry singlets. And going to the Coulomb branch, we've broken the R-symmetry. That's a typical feature that's also known for the Yangian generators. If you act on a cyclic quantity, so on a trace, like in the Lagrangian, then due to this ordered bilocal sum, it's typically not well defined. And this is what I meant in n equals 4. It's well defined because the dual Coxeter number is 0. And this gamma deformation would be well defined because you have R-symmetry singlets in the Lagrangian, which we don't have on the Coulomb branch anymore. So we have to somehow find a workaround this point. And what we did was to somehow ad hoc introduce this operator Q that breaks up the traces by averaging over all cyclic permutations of the fields. Yeah, so we introduce this Q here, and we now define the gamma deformed Coulomb branch theory by first acting with Q, then with the gamma deformation, and then closing the traces again. And then we proceed as in the massless double scaling limit and can take these gamma parameters to I infinity and the coupling to 0 and find some other theories. And in the simplest case, this leads to exactly a theory that we like because it has this difference mass structures here. It has still this 4-point vertex. So you see the first line is really just the massless Fishnet theory. And now we add this difference mass propagators for the fields X and Z, which we all have.
Don't want to be one of those annoying people, but what about double trace term?
Okay, it's true. For the moment, we just ignored them. These terms, we haven't really looked at them in detail. We wanted to arrive at this theory. It's well possible that we need additional double trace terms, as in the massless case, where they have been added later. And yeah, this is really something one should investigate further. But yeah, well, one step after another. So to find the same analogy or correspondence between scattering amplitudes and individual Feynman graphs, we take a particular planar limit or particular VEF configuration on this Coulomb branch, where we choose a finite number of these diagonal VEF entries to be non-vanishing, and for NC to infinity, an infinite number to be vanishing. This has been studied already in the context of n equals 4 in the Coulomb branch. this particular configuration. And if we define the planar limit in this way and now take NC to infinity, then because we have to sum over the fields that propagate here in the loops, the internal contributions will be dominated by the vanishing masses, yeah? Which means that the Feynman integrals that come out, that contribute to the resulting scattering amplitudes, only have internal propagators being 0. So these are exactly the integrals that we found to have this Yangian symmetry. And these are also the integrals that survive in this limit before considered in n equals 4 on the Coulomb branch, which were known to have this massive dual conformal symmetry. So if we define the planar limit in this way, we have exactly this one-to-one correspondence between this Yangian invariant massive fishnet graphs and scattering amplitudes in this particular theory. And in this sense, we can say that this theory has similar integrability properties as the massless fishnet theory. As in the massless case, this is not the only limit one can obtain in this way. We can take different limits. For example, we can define 3 couplings in this way. So here we have a GG and here we have a G square. So this is somehow unsymmetric. Take again this double scaling limit. And this yields a Lagrangian, which is composed of these 2 contributions here. So now we have 3 scalars, 2 complex scalars, x and z, and 1 real scalar. We have again this 4-point vertex, but now we have additional terms that are proportional to the masses. Yeah? So this lambda here is a diagonal mass matrix. We can choose some of the masses to be 0. So if I take the mass to 0, this contribution will be 0, which means that the scalar y decouples, and we are back to the massless case. And I think in the massless case, there are no there's no such limit which only 3 scalars. So this is, I think, a new feature to the massive situation, because as you see here, the 3rd scalar is coupled by this mass term. So you have here the mass terms for x, z, and y. These are these difference mass terms just written in matrix form. And here you have 3-point vertices, which are also proportional to the masses. And we haven't really analyzed this theory in more detail. We have just given it as an example that can be obtained as another double scaling limit, and would be very interesting to see if also this theory has some integrability features, whether it gives rise to amplitudes or Feynman graphs which are Yangian invariant, or whether integrability can be seen in some other way. And if this is the case, then we would have a second example of such a limiting theory, which would be integrable. So if we then look at the bigger picture, we have planar n equals 4 massless, which we know is integrable. We can take the double scaling limit, have the massless Fishnet theory is introduced by Volodya and Ömer, which we know is integrable. We have seen that we can write down this massive Fishnet theory, which we know is integrable in the sense that the amplitudes are annihilated by this massive Yangian, which poses the obvious question whether Coulomb branch n equals 4 super-Mills theory could also not be integrable, and whether this has maybe just not been seen so far. So this is a natural, obvious next question to analyze. So let me summarize what I've told you. So we've seen that these massless Feynman integrals inherit a Yangian symmetry from n equals 4 super-Mills theory. Somewhat surprisingly, we found that also in the massive case, we can formulate such a Yangian for Feynman integrals, which can be traced back to this massive generalization of the momentum space conformal symmetry, which maybe has not been seen because it has this slight non-locality in the masses. We've seen examples where this allows to bootstrap Feynman integrals from scratch. And we've taken this Yangian symmetry of massive Feynman integrals as a motivation to define this massive Fishnet theory, to really work out a procedure how we can define it as a double scaling limit of n equals 4 super-Mills theory. Well, there are many interesting next steps one could take at higher loops. this massive symmetry was just a conjecture. It would be nice to find a proof for it. It would be nice to further explore this idea to bootstrap Feynman integrals using the Yangian. How efficient can this be at higher loop, for higher loops, for higher loop integrals, to see how this interplay works between the series representations and, say, polylogarithms or their extensions. We've seen that this double scaling limit does not only yield this Bi-Scalar massive Fishnet theory, but also other versions with other field contents, as have been appeared in the Massless case. So an obvious question is whether they also have integrability properties. As Kolya and Amit have shown, there is this dual picture of the fish chain in the Massless case. Maybe one can generalize this also to the massive situation. And finally, yeah, perhaps the most interesting question is whether n equals 4 on the Coulomb branch can also be shown to be integrable in a similar way, maybe finding some Yangian symmetry for massive amplitudes in this theory. So that's what I wanted to say. Thanks for your attention. And if you have more questions, I'm happy to discuss.
Yeah, thank you, Florian. Thanks, Florian. And actually, we're already slightly out of the time. So let's ask 1-2 quick questions, and others we can postpone to the non-official.
May I ask?
Yeah, sure.
Florian, so you discovered the whole set of vacua, which, I mean, you started from the vacua of n equals 4, gamma deformed, and indeed you found how to say, a big family of this vacua, yes, by this symmetrization. You are sure that these are the vacua of original theory, yes? Gamma deformed.
You mean of Coulomb branch n equals 4?
Yeah, okay. So gamma deformed, it's for sure something, those are vacua, yes, even with gamma deformed case.
Gamma deformation depends on which vacua you take, so I think it's more subtle.
So at least, do you have some large class of vacua which survive the gamma deformation, yes?
No, we haven't made a similar analysis as you in your paper for all of the spontaneously broken fishnet theory. For us, the motivation was that we get the right massive fishnet theory, which gives the right Feynman integrals, and this is what we take as an input. I think the Coulomb branch n equals 4 needs further investigation. We know that this limit gives a nice theory which gives amplitudes that have Yangian symmetry. We haven't in detail looked at the vacua of this gamma deformed.
So it's not the statement that you started from the right vacua.
No,
which
I don't want to claim this. No.
So in other words, you can start from massless fishnet and then do some web and get your Lagrange.
That's what we did.
Go through n equals 4.
That's what we did with Shaposhnikov.
That's this alternative idea, right? This is this left branch, but it gives different propagator structures. It gives these propagators. So it's not really the theory which fits the Feynman integrals we've looked at. So it's a different thing. Yeah. That's why we actually came to this right branch. Yeah.
Of course, it would be good. It would be good to start from real vacua if there are some. I believe there are some of the original theory to be sure that you are
to further investigate the vacua of the Coulomb branch theory of the Coulomb branch.
Yes. Yes, that would be.
So the original theory. What do you mean by original? Which one?
Just
is
the fall in the gamma deformed n equals 4. Does it have some vacua, though it should be?
But the way it's deformed is a bit non-standard, right? As I understood, it's not just...
Right. We introduced this particular ad hoc trick here with this operator Q. This is something we do because we see that it gives the theory which has nice properties. It would be good to have another justification for why this operator Q is the right thing to introduce here.
This kind of generalization of initial prescription, right? What you say, because it works now without traces. That's what you want, right?
It's not the
or the
original
gamma deformation.
Right, it's a generalization of this original gamma deformation. We have to insert this operator Q here. The original gamma deformation would just be generated by this P gamma.
Once again, why to symmetrize here?
Because this P gamma is not well defined if you act on the traces in the Coulomb branch Lagrangian, because you need to act on asymmetry singlets. Otherwise, it's not well defined. It's this bilocal operator or bilocal phase, and this phase is only well defined if you act on an asymmetry singlet. So we had to find a way to make it well defined.
This one's a quick question, I think.
Yeah. Other quick questions?
Sorry.
What about a three-dimensional case? I mean, beginning with the ABGM theory?
The ABGM theory.
ABGM. Well, yeah, I expect that one can do a similar thing, just because we've seen that in the massless case, the generalizes quite straightforwardly, right? But we haven't looked at this explicitly, no.
Okay, thanks.
Okay, good. So let's thanks Florian again.
Yeah, so I will stop recording.